It's one pass.
Okay, so maybe let's get started. It's our pleasure to have Elie Casbi from Max-Planck-Institut for mathematics to talk about
yes, equivariant multiplicities and representations of quantum mathematics. Let me write it down. So, thank you very much for this very kind invitation. Pleased to be here in Cambridge. And right, so this is my title today. And so, at first sight, it's not clearly related to cluster algebras, but it will be. So I will explain how and so how we use this cluster structure of certain commutative rings to relate these two things. So this is going through this. So what we did, so okay, so my plan would be as follows. I will start right ahead with some cluster structures of coordinate rings. Which are probably historically one of the first examples of and then I will mention various interesting bases of these rings, and in particular, that we will one of them which will play some role in this talk is the Mirković-Vilonen basis. And then I will talk about equivariant multiplicities. And then I will explain how we can understand this cluster structure in terms of representations of quantum affine algebras. So maybe I could say category recognition of coordinate rings via representations of quantum affine algebras. And finally, I will explain our construction and results. Yeah. This is not really essential. Okay, so here we start with some finite tightly algebra G. And we have we choose some triangular decomposition, so we have Equivariant, and we denote by G and N the corresponding Lie groups. And these so-called coordinate rings, which we will be interested in, is the ring over the numbers maybe of regular functions on N. Okay. Right, so this is a very honest commutative ring, and so it was shown that to have a cluster structure. So I will explain briefly how it is constructed. So you can recall we are in finite type here, so I can choose W0, the longest element of the value group of G, and I can pick up my favorite reduced expression for this value group elements. Right. And then starting. So this is like a word on the alphabet. This is Dynkin, and of length equal to the number of positive roots. And from this data, you can construct totally explicitly. Shortly comment on me. You can construct two things. You can construct a quiver. So an oriented graph with R vertices with R there. So R is the length of this. Okay. And no loops and no 2 cycles. Okay, just by reading this word, you can construct it. And you can also pick up a bunch of very gentle regular functions on this C group. And these guys are called, so they're kind of particular good choices of regular functions, very natural choices, which are called stagnants. So this name, because for instance, in simple cases, so like in type AN, this group is a group of upper unitriangular matrices, and so this function would send some matrix like this onto certain units. So they are like superkind functions. Right. So this, and so the theorem due to the Baumann-Kamnitzer-Knutson is that this C of n has a cluster structure with initial C given by this initial, yeah. Okay, so these guys are called, so in general, it can have infinitely many seeds. It's an infinite type, usually. But you always have this kind of finite family of nice seeds, right? Which are called standard seeds. And we'll see later that from a categorification point of view, these seeds are kind of well behaved. So there is kind of, when doing some representation theory over this, it seems that there is this kind of, I don't know, belief that certain seeds are better than others for representation theory purposes. And yeah, so this is what we'll explore this one. Right, and so once again, there can be many complicated cluster variables here, but here we get this. There's all this family of kind of special cluster variables. Okay, right, and so so this ring. So actually, so the study of this kind of thing, or a quantized version of this, was one of the motivations of Hernandez-Leclerc for the introduction of this algebra. Because so in the 90s, there was a construction due to Kashiwara and Lustig of some good basis, so so-called pure canonical basis in the terminology of Lustig, and upper basis in the terminology of Kashiwara. So they constructed this basis at the level of the quantum group, or quantized quantum rings, but it descends to the basis of this complete ring. And yeah, so these bases have certain nice combinatorial properties, and understanding these properties was one of the motivations for the introduction of algebras. So yeah, so this will be the first. So there are then afterwards there were many interesting bases of this ring that were discovered, and another one that is very interesting that we will be interested in here is the so-called Mirković-Vilonen basis. Which I will now explain how it is constructed. So it's constructed from some geometry of the affine Baumann. Okay, and so there are others, right? The theta basis, the dual semi-canonical properties, etc. But so far we will be focusing on these two guys. Right. So let me now briefly explain how this thing is constructed. So it's constructed via the so-called geometric syntactic correspondence. So the story is the following: we have this E group corresponding to G, and so actually, in most of the following of the story, we will be in simply laced types, but let me just put it in a more general setting for a few minutes. So we look at the geometric objects that counts here will be the affine Grassmannian of the Lagrange dual of G. So this thing is what is defined as the quotient. So you take the k points of this Lagrange dual by the O points, where O is this ring of formal series in some indeterminate, and K is its field of fraction. Okay, so this is called. Okay. Okay. And right, so you have. So I can already mention, because it will be very useful in a moment, that there is a natural action here. So we have this G, so we can, as usual, we can fix a Borel and a maximal torus. And then we have the Lagrange dual. And there is a natural action here of the Lagrange dual of T. Okay. So there are maybe some fixed points of this action. And the fixed points denoted are parameterized by the weight lattice. They are usually denoted by L1. So the co-weight lattice of G dual, which is weight lattice. Okay. And the point is that this MV basis is constructed, is kind of parameterized by certain interesting irreducible components of this thing. So how does it work? The point is that so the construction due to Mirković-Vilonen is the following: is that for any weight, so for any dominant weight lambda and any weight mu, they constructed, they explicitly constructed, so I'm not going to write the construction here, but let's say there exists, so an explicitly constructed closed subvariety of this affine Grassmannian, so which is, I will denote by MV of lambda and mu, such that the homology space of this subvariety. So there is an isomorphism of vector spaces between this homology space and the mu weight subspace of L of lambda, where L of lambda is, as usual, the highest weight irreducible representation of G of highest weight lambda.
So you count the homological space of all degrees, or some
there is some, we choose some, like there is some 1 degree which is essentially more interesting than so lots of degrees are 0, and there is some kind of top degree which is non-trivial, and this is the one where I don't write maybe the explicit.
Can you show an example for SL2?
So for SL2, let me see. Like the explicit construction of this, I wouldn't be able to tell you. I'm not sufficiently skillful in geometric syntax, but I guess the MV basis would be in that case. Yeah, I think in that case it shouldn't be too hard, but yeah. Yeah. So essentially, this lambda tells you like this lambda is a choice of orbit. So here, this decomposes as orbits because there is a G change action. So this lambda means okay, we are looking at some orbits or closure of orbits lambda, and then mu is like you intersect it with some attraction set with respect to the action of another group.
So this is you could call it a slice in the affine mathematics.
Right. I see.
Associated into co-weights rather than weights. You said weights.
Let me see.
The weight of G, co-weight of G. How many do you?
I think they're both weights. I think they're both weights. I mean, co-weights of G. Yeah. So I don't know if that answers the question.
I have an idea, but we can. I don't want to interfere.
Sure. Okay. Anyway, yes. So the point of this statement that I will need is that here you have a natural basis, which is given by the classes of irreducible components. So here you have a natural basis.
So you're actually taking top degree.
Right. And so, of course, via this vector space isomorphism, you get a basis of this space. So then you can kind of concatenate this basis to get a basis of this guy, which is also the MV basis of L of lambda. And then there is a classical embedding of this L of lambda into this coordinate ring theory. So it's not so trivial, but you can construct a basis of Cn called the MV basis. So which is parametrized, so BC, and which is parametrized here by so-called Mirković-Vilonen cycles. Which are these irreducible subvarieties of the affine. Right. So the point is that this basis here is in general very complicated to compute, and it's very interesting. And in my knowledge, it's still open. What are the links with cluster structure Cn? So, for instance, I think it's still open that cluster monomials belong to this basis. So there has been maybe some partial steps in recent work by Baumann-Kamnitzer-Knutson. But in general, yeah, it's a difficult question. But in the recent work, Baumann-Kamnitzer-Knutson provided some tools to to study this basis from the geometry of these cycles. So this is where the notion of equivariant multiplicities come into the game. So in fact, so use equivariant multiplicities of these irreducible closed subvarieties of the affine Grassmannian. So in fact, it's a quite general notion. They just applied it to this specific context. So the general, in its very general version, you just have some closed scheme, closed projective scheme, with an action of an algebraic torus. So you have T acting on X. Okay. You need maybe a couple of mild technical conditions on the set of fixed points. Like they have to be isolated and non-degenerate or this kind of thing. I don't want to get too much into the details, but you have some set of fixed points. Okay. So I write some conditions. So under some nice conditions, you have that you can look at the T equivariant homology of X with respect to this function. And then it's theorem. So maybe it's due to Brion. I'm not, yeah. It goes quite backwards in the literature, but let's say. So that space as a vector space has a basis formed by the classes of these fixed. Okay. And so the equivariant multiplicities are just the coefficients of certain elements with respect to this basis, right? So you can take Y inside X, some closed subvariety, closed T-stable subvariety. And then you can look at the class of Y inside this homology space. So you can decompose it onto this basis. So eventually we'll get some coefficients, and this is so-called equivariant multiplicity of Y. So and so this coefficient lives in some. So we can say we can have a more precise version, but let's say for us it will live in the fraction field of C of T. You can say more precise, but let's say, yeah. Okay. For us, it will be sufficient. And so what Baumann-Kamnitzer-Knutson did is that they looked at this geometric invariance in the case of MV cycles. So this gives you kind of local information on the geometry of these varieties. And they related it to the behavior of this basis inside C. So their theorem is as follows. I mean, one of the theorems.
You need to
Sorry.
interact all the way to.
It's good. Yeah. So the theorem is that they construct some morphism. So maybe I don't write the explicit definition, but there is an explicitly defined morphism, which goes into some field of function, which for us here, so it's this field. for us, it will be, you have to think as an honest field in n variables. So you have to think like, these are the simple roots of G. And you think C of T as this field, you think of these simple roots as just some variables. So we land in this field. And the theorem is that this is an algebra morphism. And the evaluation of these guys on the MV basis is given by this equivariant multiplicity of Z at a certain point. So this one of these fixed points up there for some mu. Okay. So what we have been interested in is, so in a previous work of mine, I started studying this morphism D bar from the point of view of the cluster structure of CN. And so I had observed that somehow unexpectedly, this morphism D bar behaves extremely well with respect to the cluster structure of CN. So I will make so I will just make a couple of reminders on this. I mean, yeah, I will not reminders, but they are this. And then what we did with Jianrong is understanding this behavior and explaining it using a certain categorification of the cluster structure via some representation theoretic tools. So what are these observations? Is that, so recall that we had, so I just erased it here, but we had, you can take a standard seed in C of n. So this seed is n. So we have for some arbitrary I, a reduced expression of order 0. So this means, okay, you have this reduced expression which gives you some quiver and n nice regular functions. And then we have that, so let me write it conjecture. Let me say again that it was proved, so I could prove it in type AN and before. Which says that something happens when you evaluate that guy on this cluster variable. So you have these flag minus, these specific cluster variables are seen. And then something happens here, which means that it's always of some kind of very distinguished form, like 1 over some polynomial, which is a product of positive roots. Maybe with some multiplicities. Right. And moreover, there are some, so these cluster variables are algebraically independent at the level of the cluster algebra. But when you land after applying this map, then, okay, maybe you're losing some utility. So, and then there are some remarkable polynomial relationships between P1 and P2. Maybe I should do this. So inside the same C. So I'm not going to write them down explicitly because it would require some boring combinatorial notations, but let's, yeah, so I'm just, right, so here, so that proof required KLR algebras. So these categorifications due to Complexified. But at some point, it didn't seem so easy to use the same techniques for the other simply based types. Moreover, the meaning of these relations remain kind of not so clear. So that was, yeah, sure.
So you have this relation on this side,
Mm-hmm.
but do they mean anything on CN, like for the cluster, right?
So, I mean, yeah, I can say one. So between the XKs themselves, I don't know. But if you want a more cluster, like there is a cluster theoretic formulation of this, which I can actually say right here. So given this seed, you can cook up some Laurent monomial in these variables, which are usually denoted by I think in the cluster literature. So you have this. Okay, you have some frozen variables, but anyway, you have some y hat j's for j exchangeable directions. And so these polynomial relations essentially are equivalent to saying that you can perform. So this is just a Laurent monomial, and you can perform that thing. This perfectly makes sense. And then these relations mean that this kind of is almost trivial. This is almost one. So this is more precisely a quotient of positive boosts on beta j out of beta j prime, with j prime explicitly related to j. So in some sense, so this means that this d bar, so this should be some extremely complicated thing, the huge numerator and the huge denominator. And at some point, every cell cancels, and you're just left with some very simple thing. So yeah, in a cluster theoretic language, these relations can be thought this way. So I think it doesn't, yeah, the xk are still independent, but it just means that when you look at these y variables or x cluster, I don't know what I should say, but yeah, these kind of y hat variables with limitations of Dynkin, then like something happens here. Right? So this d bar is particularly well behaved on this side of the right. More actually, yeah. All right. So with Jianrong, we decided to.
Sorry, this is the same J, right?
Here is the same J.
As above.
As here,
Yeah.
and as here, yeah, yeah. Yeah, so with Jianrong, we decided to use this categorification due to Hernandez-Leclerc, which is known to be very well suited with respect to the class of structure. So I will need a couple of reminders on this. Yeah. Okay. So this quantum affine algebra is so it can be viewed as a deformation of the universal enveloping algebra of G hat. So we have this Katz-Moody algebra. So G is still finite, like maybe in ADE, but. And we can look at this universal enveloping algebra of G hat, which will be a affine Katz-Moody algebra. And this quantum affine algebra can be viewed as a two deformation of this. So this is quantum affine algebra associated to G. And we are looking at finite dimensional representations of this guy. So C, category of finite dimensional representations of this thing. So this is usually this is an extremely complicated category. This is a monoidal category, but very complicated. It has a lot of simple objects. Right. So, but one good thing is that there is character notion. So we can understand these representations inside some torus, and we can do some computations. So more precisely, there is this construction due to Frankel and Dynkin, which is the so-called q-characters. So there is an embedding of this. So this is monoidal. So we can look at this Grothendieck group, which is a ring, commutative ring. And we can embed it into some torus. Right? So we can make computations here rather explicitly. So it's an algebra morphism in the ring. And this torus is so this is like to tell you how huge this category is generated by some guys, right? Some variables, y, which are in bijection with so I is in the Dynkin and A is a non-zero complex number. So this is a massive torus. And the simple objects here are in bijection, so symbols, via this in some sense, this embedding, are in bijection with monomials, like honest monomials in these Y's. So that makes a lot of symbols, of course. So this is far, far too big for us.
But it's like the image is not the normal. It's just leading term, isn't it?
I mean, if you take the whole q character, so yeah, so this induces a bijection at the combinatorial level. But then, of course, if you look at chi q of some symbol, then you will get m plus some other terms here. Right. So Hernandez-Leclerc looked at certain kind of discrete skeleton inside this category. So we don't care about all of this. We will care only of a countable collection of these generators. Okay. And this will be the category we will need to see the cluster structure of C. So cluster monomials will correspond to certain specific simple modules here, or certain specific monomials. So now, so recall that G is AGE here, so we can choose an orientation of this Dynkin graph. Choose your favorite orientation Q. And I will need also a height function, which means that adapted to Q. So I have, you imagine you attach an integer to each node of the Dynkin diagram, such that psi of j equals psi of I minus 1 if there is an arrow from I to j. Okay, so you can associate a value to each node of the Dynkin graph which sees Q, which is compatible with Q. And then we look at some subcategory here. So we have this C. Okay. Here. And we have some we have some category which will denote C minus, okay, which is generated by some torus. So yeah, let me write Z to insist on the fact that it's kind of countable version of this, right? So which will be generated by, so you just pick up some nice family. So I is I, but A will be always a power of Q. So an integer power of Q. And this integer should be smaller than psi of I by an integer number, by an even number. So it doesn't really matter for us, just the definition. Don't worry too much about it. It's just some nice countable collection of geometries. What is more important for us is that there is kind of so there is a kind of finite parts in this collection, in this countable collection, which they call CQ, which only depend on Q essentially. So, okay. Yeah, actually, I don't know one thing. So this will be some kind of little finite bit inside here. And the theorem due to Hernandez-Leclerc is that there is an isomorphism. Maybe I should. So there is an isomorphism. You see, so that's. But there is more than that. So this isomorphism has two nice properties. So the first property is that it induces a bijections between simples and the dual canonical basis. So the first basis I mentioned at the beginning of this talk. And the second property is that these cluster variables here, so this flag minors, so x1 I, xr I. If you choose I to be adapted to Q, so we have this orientation of the Dynkin diagram. This, by some combinatorics, give you some nice reduced expression on W0. Then those cluster variables are explicitly understood here at the level of the category. So they are certain simple modules called Kirillov-Reshetikhin modules. Whatever they are called, what matters for us is that we know them completely, right? They are very well-behaved simple objects. And that will be actually the advantage of this approach compared to this scalar thing, is that we have a clear description here of certain, at least of certain of these specific cluster variables or cluster monomers. Right. And so cluster mutations from the seeds are interpreted at the level of character of modules, etc. All right. So I think, yeah, now I can do the last part. So I'll need just a couple, sorry about that, a couple of more notations before saving the constructions. Okay, so there are two things. So essentially, the idea is that we will construct some map from here to what we want, to the field. So we'll construct something here. And the idea is that when you restrict it to that thing, you should obtain the morphism earlier mentioned. So the construction goes as follows. We use certain family of integers called inverse of quantum control matrices. So in the AT type, they are not so hard to define. So you have the Cantor matrix of G, which is this nice Cantor matrix, and you can define a slight deformation of this, which is just the same as the Cantor matrix, but you put some Z plus the inverse instead of 2 on the diagonal. This matrix is given by Z plus the inverse on the diagonal, and just the normal thing out. Okay, so this is very easy. And this matrix is invertible. Invert it. Okay, and you can look at the ij entry of this inverse, which I denote this way. So that one can be complicated, but so you can expand it into theory. And these are the coefficients we are interested in. So it's just a bunch of integers, infinite families of integers, entirely determined by your choice of G, by the Dynkin. Right, and so these are the ones that are involved in it. The second bit of notation, second and last bit of notation I need is a little bit about standardized theory. Why is it? So Austin-Island theory, because we have this orientation Q. So we have this, I will denote by gamma 1, gamma n, the dimension vectors of the injective indecomposable, so gamma j. So dimension vector of injective indecomposable of Q. And then there is a classical fact that you can perform the Ausländer-Heidelberg translation on this guy. So I really know tau. So I will always stay at the level of dimension vectors, so it's the Coxeter transform. Coxeter transform. And then when you look at this fact that positive and negative roots are given by iterative application of this. I think this is all what I need. And now I can say what is our construction and state. So as I said, did I erase it? No, I didn't erase it. So we define the morphism. So in fact, to be more precise, our morphism will be defined on this bigger one rather than on this. So you can always restrict it to this one, but in fact, we define it here. I declare what should be the image of each generator. Okay, so the image should be somebody there. Okay. So in appearance, it will be an infinite product, but in fact, it will be finite. Once you fix I and P, it's finite. So in product over all the JS satisfying this function. So this. Of this these positives here, sorry. So let me write it correctly. These positive roots. And the multiplicity of this positive root in this product will be given by some linear combination of these coefficients. Right. Okay, maybe I don't write it explicitly, it's not so necessary, I think. Yes. Okay. So whatever the formula is, the point is that for each generator, you associate some a priori infinite, but in fact finite, some product of positive roots because you have this bijection. So maybe each positive root will appear probably many times, but that doesn't matter. And we use these coefficients here. So it's finite because when S becomes very small, these guys will be zero at some point. So only a finite number of couples will have some non-zero thing, non-zero. So in fact, for each YP, in fact, it's a finite product. So no worries of definitions. And so our result is that okay, so you have this cluster algebra Cn with this morphism due to Baumann-Kamnitzer-Knutson, and we want to understand its behavior with respect to the cluster structure of Cn. And here you have Hernandez-Leclerc isomorphism, right? Here you have this q-charactermorphism, YQ. And our morphism lives on this torus, so you can restrict it to YQ. And our theorem is that this states. So the restriction of this thing to the cluster algebra we want to study coincide with the morphism defined by Baumann-Kamnitzer. And as a corollary, we can obtain the conjecture we wanted. Is that is the conjecture stated or liberty stated? Let's see. The point is really that these flag minors here are nicely understood as certain nice modules here. And because the characters of these modules are well behaved, this definition in this setting implies so once we know this kind of follow with it. How much time? 5 minutes. Okay, so then to conclude, I can just mention a couple of questions. Our All right, so maybe I can mention two questions. Okay. So the first, let me check. So first question that we would like to study in the future is that right. So recall that we have this in this picture. We have this embedding here. Okay. So I just raised it, but there was this bigger category. There was this bigger torus. And our map, in fact, is defined here, right? So this guy is just the restriction of it. And the point is that that thing was actually a bit later than this. It was also proved by Hernandez-Leclerc to be a cluster algebra. And that thing is isomorphic to some, I don't know, so it's a theorem due to Hernandez-Leclerc as well. That this Grothendieck ring has a cluster algebra structure. So it's a little bit complicated because it has infinite rank. So there are infinitely many cluster variables in each C. But the point is that now, using cluster mutations, we can obtain a lot. We can study this map on this cluster algebra and using it's a morphism. So we can use cluster mutations to obtain lots of values. Which this morphism cannot see, right? Because it is only in this little part. But using this cluster structure on this bigger part, we can obtain new values using cluster mutations. And so then there is a natural question to ask is that from Baumann-Kamnitzer result, we know that evaluation of this guy on a certain basis encodes certain geometric informations of MV cycles. So then the question we are asking is there an interpretation? So a geometric interpretation of these values. So is there, so we have this geometric attack here, and yeah, the question is, in an example, it suggests, yeah, so at least certain values, so maybe that could be a good basis of this much larger cluster algebra, such that the evaluation of this map here could have some geometric meaning in terms of equivariant multiplicities. And maybe I have 1 minute left. So the second question we would like to ask is the following: is the relationship, maybe connection, with the quantum cluster algebra structure of the quantum, of a quantum deformation of this guy, which is usually denoted by Elie Casbi, so-called quantized portentry. And there are maybe a couple, like maybe one motivation I can quote for that is that these coefficients appearing in our definitions on this thing. These things, they are precisely the same as certain, how to say, they are precisely the same as a certain so-called QT character theory of Hernandez-Leclerc. And so you can obtain, via these things, you can obtain the quantum torus. Encoding the Q commutations of the cluster variables of this initial seed. So you have this, you have these flag minors there. Yeah. And so in this quantized cluster algebra, they Q commute inside one same seed. So you have some quantum torus encoding these Q commutation relations. And this, so it's a theorem by Hernandez-Leclerc that this Q commutation between these variables are given by these coefficients. Quantum torus of the which is kind of surprising because a priori all of this story is commutative, but at some point it seems that this quantized plus algebra structure is kind of more or less encoded in this story. So maybe I should stop. Thank you very much.
Is there any questions? So let's see. I mean, so is this commutativity of this diagram be helpful for comparing the NV basis and the canonical basis? Dual canonical basis?
I believe so. So I think it's already known that these two bases are different.
But at least for the cluster monomials.
Right, at least for the cluster monomials. Then right, we shall need a clear understanding of this of the behavior of these maximum cluster monomials. So we have some, let's say, some partial results on this. The point is that it's not injective, which makes things a bit.
You mean this map D bar is not injective?
Yeah, both of them, like this one or this one, they are not injective. So at some point we are losing some information. So that makes things a bit complicated. But usually yes, like this map was also constructed as a powerful tool to compare bases. So for example, they use it in their paper, in an appendix of their paper, they use it to prove that the MV basis and the dual semi-canonical basis are the same. So it can be kind of indeed a useful tool to do this, to prove this kind of things. But they don't use it for from a cluster perspective. So they don't do that. That's I believe it could be a very useful tool, but so far we don't.
So you said that, so they prove dual semi-canonical bases and ME bases are the same.
Are different. Yeah,
so they prove that.
You can prove that it's not the same because you have like elements which are at the same point in the crystal structure, so they should satisfy. So if it was the same basis, there should be the same elements, but they have different images by this thing. So you can,
What types?
I think so, yes. Let me see. At least in type A for sure. But maybe the arguments can be, because I think at some point, they provide some explicit computations. So, but I think it works for all types. Right. No, I think it does.
Okay, if there's no more question, let's thank Elie Casbi again for your talk.